Okay, so in this video, we're going to go over the most important relationship with respect to gases, which is called the ideal gas law. It's extremely useful, very powerful, and pretty accurate under most conditions, most experimental conditions. We'll get into all the nitty-gritty details in the following videos. What this equation is going to do, it's called PV equals nRT, or some people call it PVnRT. It's going to relate the four different variables of gases, which are pressure, temperature, volume, and the amount of gas. And the amount of gas, when we talk about the amount of gas, we really care about not so much its weight, although we can calculate that, but we care about the number of particles, right? So in chemistry, the counting unit is the mole. So if we want to count in a very easy way the number of particles, we're going to use the mole because that connects, remember, the microscopic atom to the macroscopic grams. All right, so here it is, PV equals nRT. This is called the ideal gas law, and we'll get into in later videos what makes a gas ideal and what cases may it not be ideal. But under most conditions, this is a very accurate equation. And so P is the pressure, so P times V. V is the volume. R is a constant. Okay, here it is. It's a known constant for these gases that's been experimentally determined. If you have an ideal gas, which most of the time you will, this constant is valid. So 0.08206 liters times atmospheres divided by moles per Kelvin. Now you can convert this constant into other units if you want, but most of the time, for most problems, it's going to be easiest just to remember this number, or if you're given this number by your instructor, that would be great. I don't really believe in memorization of numbers like this. I don't think it's that useful. But if you get this number, then you're going to want to use your pressure P in atmospheres, your volume V in liters, your N is going to be your number of moles. And your temperature, it's really important that your temperature is in Kelvin. It has to be in Kelvin. Common mistake students make is that they leave their temperature in Celsius. And so you know how to convert from Celsius to Kelvin. You add 273.15 to go into Kelvin. And we'll do lots of practice in the next video on that. So PV equals nRT. So if we divide by by NT, okay, so we divide both sides by NT, what we get is R. Okay, we get that constant. So it's just experimentally determined that the pressure of an ideal gas times its volume divided by its absolute temperature in Kelvin, and it's the number of moles of it is always equal to the same value of R, this 0.08206 liters atmospheres moles Kelvin. And that's true at any one state or any second state, right? And so they're both going to equal to R. So we can come up with this relationship for a gas that's changing states. Maybe the gas is being compressed, or maybe the gas is being heated, or more gas is being added to your container. You can get this relationship P1V1 over T1N1 equals P2V2 over T2N2. And so here we'll just call 1 the initial state of the gas and 2 the final state of the gas. So you'll use this expression if you have a gas that's undergoing a change. If you don't have a gas that's undergoing a change, chances are you're just going to use PV equals nRT. Okay, so that's how this works. They're both equal to R, so they're equal to the same thing, so they're equal to one another. And now we're just going to go through a series of different relationships while we hold the other two variables constant. So we're going to be changing one variable, holding another two variables constant, and looking at the fourth variable. How does that change? So what happens if we change pressure or volume and we keep the temperature and the number of moles in the container constant? Well, this is called Boyles Law, and it's pretty intuitive. If you increase the pressure, you're going to decrease the volume. You're squeezing the gas, you're squeezing that container and making that container smaller. And it's a linear relationship. So if you double the pressure, you half the volume. If you double the volume, you half the pressure. Okay? And so it falls right out of this relationship we just showed, this changing equation. But now T1 and N1 are the same values. So if T1 is equal to T2, well, the same thing on the left-hand side as the right-hand side, algebra says we can cancel it out, right? And N1 equals N2. So we can cancel out these grayed out variables, and we end up with just P1V1 equals P2V2. So you can memorize that if you want. I would just memorize PV equals nRT. And very quickly, you can get from there, right? You just look at this, PV equals nRT. Oh, I know PV equals PV, basically. P1V2. P1 V1 equals P2 V2. Okay. So that's Boyles law. Charles law, this is the relationship between temperature and volume. So we're going to keep pressure and the amount of moles constant. And so this is the hot air balloon type experiment. Or if you put a balloon in a bucket of ice or in liquid nitrogen, it shrinks, and very dramatically so in the case of liquid nitrogen, because liquid nitrogen is so cold. So if you heat something up, it's going to expand the container. The gas is going to want to take up more space if the pressure is the same, or if you cool the gas down, it's going to shrink. The gas is going to take up less space, and so the volume is going to decrease. And again, it's linearly related. So if you double the absolute temperature, now the temperature in Kelvin, not in Celsius or Fahrenheit, it has to be in Kelvin, the absolute temperature. And we'll talk about why in a bit. But if you double the absolute temperature, you'll double the volume. If you half the volume, you will half the temperature. Okay, linearly related. And again, it comes from this relationship. Now, our P1 and our N1 are constant in this case for Charles' laws. And so they cancel out. And so we're left with V1 over T1 equals V2 over T2. Again, you could memorize that. I don't think you should. I would suggest you just memorize PV equals nRT, and then very quickly you can say, oh, what's constant? N and P, I'm changing volume and temperature, so I want V divided by T, get that on the same side. That's going to equal V divided by T with the 1s and 2s. Okay. So this is the pretty cool thing. This is where this concept of absolute zero by Lord Kelvin was first discovered or invented in some way. It's a concept was invented, but it seems to be a truth that you can't go lower than 0 Kelvin, right? That this is the coldest temperature of the universe. And this is where molecular motion theoretically will stop. Now, we know because of the Heisenberg uncertainty principle, and go to the quantum mechanics lectures for a talk about that, but we know from the Heisenberg uncertainty principle that you can never know exactly where any particle is. And because you never know exactly where any particle is, then they can't be completely stopped. Because if they're completely stopped, then you would know where they were exactly. And if you knew where they were exactly, you'd be violating this principle of quantum mechanics. And so for that reason, you can never achieve 0 Kelvin. But you can get very, very close. People have gotten down to nano Kelvin now fairly routinely with some laser cooling experiments that are a little bit exotic. I believe they've even gotten more recently down to picokelvin, which is pretty impressive, but it takes a lot of energy to suck out all that heat. Okay. Liquid helium, which is kind of the lowest common temperature that's achieved, is around 4 Kelvin. So that gives you an idea. So 4 Kelvin, that's negative 269 degrees Celsius. But anyway, where this idea came from of Kelvin, of 0 Kelvin that Lord Kelvin discovered, is he just measured using Charles' law the volume of different gases, and then he just extrapolated the line down to 0. Now, of course, you can't have he didn't actually do these experiments at 0 Kelvin or close to 0 Kelvin, but he just saw, well, where would the volume theoretically be 0 of the gas? And a gas, its volume would theoretically be 0 at minus 273. Now, far before that, it would liquefy and then solidify. But theoretically, if you had a gas that didn't liquefy or solidify, 0 Kelvin would be the point at which is 0 volume. So really, really interesting, beautifully simple and elegant experiment to get to one of the most profound conclusions of chemistry and physics. So the last one is Avogadro's law, and this one is just your chest expanding in and out. You inhale, more air, your chest gets big. You exhale, your chest gets small. Why? Because it's changing the amount of moles, the amount of gas in there. So obviously, as you increase the amount of gas, your volume is going to increase, and vice versa. And again, you get this from this relationship. Now pressure and temperature are constant, so they're grayed out. And you just get V1 over N1 equals V2 over N2. It's called Avogadro's law. Don't memorize it, derive it very quickly from PV equals nRT. So if the conditions are changing, in summary, use this P1 V1 over T1 N1 equals P2 V2 over T2 N2. And take careful note of what things are constant. Now, maybe all 4 variables are changing, in which case none of these would cancel out, and you'd have 8 numbers to deal with. That's fine. You'd have to know 7 of the values in order to calculate the 8th, right? But you could do that. If you're not changing, right, if your conditions are constant, you're going to use PV equals nRT, or this rearranged version. This is also fine. And so this is just another way of showing you when they're not changing, right, how you can get back to PV equals nRT from this, okay? So it's just canceling some things out and getting back to PV equals nRT. All right, so in the next video, we're going to do some practice problems on PV equals nRT, changing, not changing type of practice problems.